Can everyone see my slides? Yes, okay, good. So just keeping an eye on the time, Chelsea, this class goes till 10:10, is that correct?
10:15, but Ramon's gonna talk for a few, or maybe 15 minutes as well.
Yeah, okay, so I'll quickly go through my slides, and I don't have a lot of them. But I wanted to give you an introduction to Pacific Gas and Electric, and I thought we could, as a group, maybe quickly go through a fault mapping example for infrastructure. So I'll just limit it to one fault, and then briefly touch upon some of the research aspects of this class that I'm excited about, that Steve will go into more detail in the next lecture. So Pacific Gas and Electric is a large utility company in California. We serve 16 million customers. Our service territory extends from just north of LA all the way up north to the Oregon border, and from the coast to the Eastern California border, except on the east side of the Sierra Nevada, where that's Southern California Edison territory. We have a lot of utility infrastructure and assets. We've got thousands of miles of electric and gas transmission lines. So these are the large gas pipelines that carry gas from city to city, or the large power lines that you see when you're driving down the interstate. And then we have tens of thousands to hundreds of thousands of miles of distribution lines. These are the lines that take gas or electricity to your house. We also do power generation. We have over 170 hydro dams in the Sierra Nevada and a couple in the Coast Ranges. And we also have a nuclear power plant that will reach the end of its license in 2025. So that will be decommissioned as we move to other renewable energy sources. So a unique thing about PG&E is we've got a dedicated geology department, a geosciences department. Right now we've got 20 personnel that includes geologists, seismologists, different engineers. And this group was formed to manage what we call the long-term seismic program for the Diablo Canyon nuclear power plant. And it's written into the operating license that PG&E needs to have a geosciences department to keep abreast of new research in seismology, faulting around the power plant, and just in general, how the science is advancing. Over the years, the Geosciences Department has broadened its role to support all the lines of business. So not just nuclear power generation, but gas and electric. We also have gas storage. And we look at seismic hazards, but all sorts of hazards, geohazards, including landslides for those different assets. And I guess this is a good time to say that this is what really excites me about geology. I like where the science is used to understand hazard for critical facilities. I think that's a great service of the science, and it's something that really interests me. So my two primary functions in the Geosciences Department are seismic source characterization or fault characterization for our hydro system. So we've got 136 faults around our dams, and we calculate ground motion hazard for the dams. And so I work with consultants like Steve to characterize those faults and calculate ground motions. I also work with folks like Rich as reviewers to the work that we do. So we bring in professors and academic experts to review the work we do. And then I also work with folks like Ramon to do research, to reduce uncertainties in hazard. And I thought this map here shows an example of our gas transmission lines in the Bay Area. So these are those larger diameter lines. These aren't the ones that go to your house. And then the faults in the Bay Area. So everyone recognizes the San Andreas here on the left, and we've got the Hayward faults and other Bay Area faults. And each of these dots is where one of those faults intersects one of those transmission lines. And under our gas fault crossing program, we study these crossings to characterize the faults, what type of faults they are, what's the exact location relative to the pipelines, what's the orientation, that's often important for gas pipeline crossings and how the pipeline will respond. And then also what the displacement will be during a large earthquake on each of these faults. And so that's the other thing that I do with PG&E. I manage the pipeline fault crossing study program. And if a pipeline is found not to have enough capacity to withstand a large earthquake, then we go ahead and do a mitigation. And we strengthen that pipeline, or we put in shutoff valves, or we make it more resilient to fault rupture. So what I wanted to do next is just a simple mapping exercise down in the vicinity of the Ridgecrest earthquakes, which I assume that you're all familiar with. There's a magnitude 6.4 on July 4th, 2019, and then a 7.1 shortly thereafter. And so this is a Google Earth image, and in yellow is one of our gas pipelines, and in orange is the USGS fault and fold database, showing strands of the Little Lake fault in the vicinity. These faults are not necessarily mapped very well. There could be registration errors. So wherever we see one of these fault crossings between our pipeline, our transmission line, and a mapped fault, we do a study in that area. And unfortunately, this area was slated for study in 2021. So we missed, we didn't have it studied before the earthquake. The pipe did fine. And the reason that it was kind of on the bottom of our list of studies was this is a really low slip rate fault system. The gas line is out in the middle of nowhere. It's not near where people live. And so that's prioritized lower compared to gas lines like in the Bay Area, higher slip rate faults, higher likelihood of an earthquake. And those gas lines are near infrastructure in people's houses. So I was hoping that people could maybe call out things that they see on this image, on this Google Earth image, that might be related to an active fault. And professors can chime in too to get things going. But we've got maybe a poorly mapped representation of where a fault could be here. And we've got some geomorphic features that are indicative of a fault zone going through this area and crossing our line. So any takers?
Don't be shy, guys. Remember, I think everyone has access to what is the annotation tools in Zoom. Like if you go up to, it says on mine, view options, annotate, and then I get these little tools. So like draw, and so I can draw a tiny line like right there.
Mm-hmm.
So, any other takers for?
I would just state, well, I mean, it's probably obvious for generally everyone here, but the transition in sediment from where the supposed fault is to where it isn't, from the north to south.
Like that, yeah. Yep, and you can see a drainage pattern. So there's kind of this north-south drainage pattern that seems to change in this area here. What draws my eye, because we're running short of time, is there's this linear feature, this linear trend of high topography here. So maybe that's what this fault was originally based on. And then there's another one over here. This feature right here is my favorite in the area. It's not tectonic. It's a sand dune created by the burrow feed in the wild burrow corrals that are just off the map. That shows you the wind direction and the impact that that has on the environment. Why don't we shift to LiDAR here? So for PG&E, we fly all of our gas lines with a 2,000-foot buffer for LiDAR. This LiDAR is actually post Ridgecrest rupture LiDAR, but the feature that we were looking at, you can see it very, very clearly. It just stands out. So these could be pressure ridges related to a fault zone extending across here. Now, for a fault crossing study where we're very interested in exactly where the fault is crossing the pipeline, the orientation of that crossing, we would do more detailed mapping based on imagery, LiDAR, historical topo maps, historical photos, like what Ramon curated in the Fairchild collection. And so the black lines here are mapping that was done by Bell, Philibosian, and colleagues after the rupture, because there weren't a lot of faults mapped down in this area. There's not a lot of interest in mapping faults down here because it's not really near populated areas. The town of Ridgecrest is to the northwest, but there was just really a dearth of mapping in this area. So they said, if we didn't know that the rupture occurred, what features could we see that could be related to active faulting? And so all these lines are theirs. They map things like tonal lineaments, changes in sediment, changes in slope. They've got these lines here that represent the linear ridges, which may not be exactly where the fault would rupture, but it just marks the general location of the fault zone. So you can see, based on the skills that you're going to learn in this class, you could map this fault zone, and you could also map other features out here. Here's some tonal lineaments out here, tonal lineament here. Here's a nice fault zone here. And then you're going to be mapping geomorphic features that represent faulting, like linear ridges. But if you can see, there's no obvious features in the vicinity of the pipeline crossings. So you might put some dotted lines. I put white lines here that would connect these different features into a fault that would rupture during the next earthquake. So now let's go to this is pre-rupture mapping. This mapping is not based on knowing where the fault would exactly rupture. It's just based on the geomorphology. Now let's go to this area right here, right after the 6.4 earthquake. And so this is a UAV image that was provided by Rich and Ian Pierce. They appeared on the rupture right after it occurred and started flying a drone around and flew everything that they could at very high resolution. The yellow line here represents our pipeline. And as you can see, the rupture is pretty complex. There's a principal trace here, but it's got a lot of en echelon steps. And there's several secondary ruptures as well. This is ground views. So I'm looking to the northwest. You see you have two principal traces here, and only one of them showed really obvious displacement, C right here. And it had about a foot in industry, we talk in feet, of left lateral displacement. And we actually opened this pipeline trench to see if it was okay. The pipe was fine, but because the pipeline was placed in the 1950s, and we sucked the dirt out of the trench instead of redigging the trench, we had the original trench walls preserved, and we were able to see the offset on those trench walls. The surface offset here was a foot of discrete offset and then a bunch of secondary deformation. The displacement of the trench wall at depth was 3 feet, or a little under a meter. So let's go back to our pre-rupture mapping right here. So these are all the lines that were mapped for that paper. And then this is the actual surface rupture. This is a data set by Ponte et al. And it compiles data from all the different field mapping teams. And you can see some things right off the bat, that the rupture generally followed this area of elevated topography and even continued here. These aren't delineated as primary or secondary traces. The primary trace continues like this. So this is a secondary trace here. This is a secondary trace here that lines up nicely with our linear drainage right here. However, the principal trace here did not line up with anything that people mapped before the rupture. And so that's a conundrum when you're working in industry. You could do a site-specific evaluation and you could do your best geomorphic mapping, and the rupture may not exactly follow your geomorphically mapped traces. This is zooming in right here of the area of the fault crossing. So here are those dotted lines that would connect different pre-rupture mapped traces. Here's the actual rupture, and you see that there's a difference. So the difference between these pre-rupture traces and the actual rupture is 10 to 30 meters in this area. And so it brings me to what I'm really excited about for this class, and PG&E sponsored the development of this class to get at some of these research questions. What is the rupture location uncertainty for faults mapped with different levels of confidence? So if I had a really nice fault scarp out in the field, didn't have a historic rupture, and I mapped that scarp, how close is the next rupture going to be to that well-mapped fault scarp versus a less well-mapped feature or a feature that is not very well mapped at all, that's just inferred, like a very weak lineament or a connection between well-mapped strands. How does this uncertainty change with climate, geology, slip rate, et cetera? So out in the desert, you really easily see a lot of the tectonic geomorphology. As you saw in this case, right at the pipeline crossing, we were still pretty far off with the geomorphic mapping. Now, something to bring up is in this area where we have these different dotted lines, those are different interpretations of where the fault goes. Those represent different models, and that's what's called epistemic uncertainty. That can be reduced with more information. So if we dug a trench across here, we could find fault traces in the trenches and better nail down where these traces are. And then what is the variability in rupture location from one earthquake to the next? So this is the aleatory variability. This is the uncertainty that cannot be reduced with more information. It's just the randomness of the rupture. So if I have a well-documented fault trace and I've got my trenching supports, the surface morphology is exactly where the fault is at depth, what's the likelihood that the next rupture is going to exactly follow that trace or be off by 5 meters, 10 meters? This isn't necessarily so important out here in the desert where our pipe sections are very straight. Pipes can be very sensitive to fault location if they have bends, if they have other pipes coming off of them. So in the Bay Area, we're really interested in these uncertainties because you're in an urbanized environment and you've got a lot of bends in the pipes and you've got a lot of things coming off the pipes. So the exact location of the next rupture really matters. So these are two tables from a figure and a table from Peterson et al. 2011 that illustrates what I was talking about. Steve's going to go into this in more detail next week, so I'll cede the rest of my time to Ramon. So yeah,
I have one thing, Chris. Can you hear me? This is Rich.
Yeah.
Just one thing for the students. I just want to mention that we the teachers of this class obsess over these details on this, like this example that Chris was showing. But for the students, you should know that like operators like PG&E and other gas pipeline, oil pipeline operators, they're really concerned with this because one of the main reasons is cost. And you don't want to have to design and use your engineers to design a special pipeline crossing for several kilometers or something like that. It just becomes too cost prohibitive. So they really want us to narrow down the location and the width of this zone of where faulting could come through to minimize the cost of special designs.
Yep. Thanks, Rich.
Do any students have any quick questions for Chris?
I have a quick question. How impactful are precipitation values on that specific location? And like, for instance, in Arizona, you see, especially if you grew up in the desert, you'll see how impactful groundwater loss is and how similar they look to fault scarps. How impactful would it be at this location?
That I don't know. I know it's a very dry environment there. The geomorphology is very well preserved in the area. Climate was more wet in the past during the last glacial maximum. All those drainages that we saw drain into a big basin, big lake. So during wetter times, you could have eroded or removed evidence of faulting. If the faults are very low slip rate, then your climate signal could be larger than your tectonic signal. That's not the case now, but it could have been the case in the past. I don't know if that fully answers your question.
No, giving a ratio like that is super informative, like especially in the case you're bringing up in the Bay Area where climate plays a huge role.
And it's really harder to see faults in the Bay Area than out in the